We're live and let's start our streaming. So let's share my screen and we have to return the length of the diameter of the tree. So the diameter of binary tree is the length of the longest path between any two nodes in the tree. So this diameter, this path may or may not pass through the root. So the length of path between two nodes is represented by the number of edges between them. So what we can do, we can, on each node, we can check the current diameter. Like if we will start, for example, with this node, so we see like 1, 2, and 3, it's actually the diameter of this one, but actually here we can have something like 1 and 1, and then we have like 1 and 1, 2, 3. So we have like 1 and 3, it would be 4. But if we will go up, then this 4 is not actually correct value. So it's not correct value, and we should return actually from here the maximum between 1 and then 3. So what we have, we can have, so we can have, for example, some integer maximum that would be 0, and then we have like this diameter binary tree, and we can, for example, use this as the recursion function. So for example, if it's 0, then we just return 0 here, and if it's not 0, then we currently on, for example, node 4, and we have left and right, so we can check this root left int left, and then we can have the same for right, and so we can check, for example, so we have left and we have right, and what we can do, we can update our maximum, mass maximum between L plus R plus 1 and this maximum. Okay. And then return maximum, but I think it will not work because let's imagine such use case. So we have 1, then 2, then here we have 3, then here we have like 4, then 5, then under 5 we have, for example, 6, and under 6 we have, for example, 7. So in this case we have 1, 2, 3, and 4. So 4 would be the result. And from here, like we have 1, 2, 3, and plus this 1, we have 4. So here it's actually 4, but we should return the maximum. Yeah, we should return the maximum from here. So it should be like mass maximum L or R plus 1. Yeah, so now we should update. So for example, here we return 0, like it would be 0. No, it would be 1 from here. From here is also 1. Then here it's 2 because it's maximum. Yeah. 1. Then here is 2 and 2 and 2 and 0. A plus 1, 3. 3 plus 1, 4. Yeah, so I think it should work. So let's check. Yeah, mass maximum. But I believe this one we should make separate function. Let's call this function DFS. And in this DFS, we just put our root, tree root, and we do this logic here. And it should be integer. And here our maximum. We update it all the time. And yeah, so let's call this one also. We should, here we just return maximum, but before maximum, we should call DFS function with our root. Something like this. So let's check. Okay, so we have 17. But result is 3. Interesting how we can get 17. L plus R. So when we on here, we just return 0, right? Then when we on 4, from here we return 0, 0. Maximum would be 1. So we update just 1. And here we return 1. So from here we return 1. Then yeah, so then we go on 2. So on 2 we have here, we have 1. Then we go on to the right. To the right we also return 1. And then from 2 we have 1 plus 1 plus 1. Yeah, I think maybe like this. 1 plus 1, it will be like 2. Yeah, it will be 2. But how it's possible that here we output 0? Let's check max. Let's check L and R here. So we will check L is equal to L plus R is equal to R. Yeah, how is possible null and 0 and 0? Because, yes. So we still need 1. Okay, so now we have 17. No, here I think we should not have 1. So when we on 4, so let's imagine here we on 4, right? Because from left we get 0, then we get 0, and max would be 0 here. We can even, I think, print here value, root value. Okay, so when we had 4, yeah, so it's 0, 0, maximum 0, but here we should return 1. So from 0 we return 1. We should get 1. But I don't understand why. Why we return 0? Because we are calling this. Okay. All right, so now it works. So we have DFS function. Let's call submit. Yeah, and we see that it works actually. Let's check our previous implementations. Yeah, so we do it the same logic here. Let's check this one. Also the same. This one, same. What about first? Yeah, also the same, but we actually don't need this stuff here. Right, so we're done. Let's go to the next one. Right, so what do we have? Given a binary tree, determine if it's a high balanced. High balanced binary tree is a binary tree in which the depth of the two subtrees of every node never differs by more than one. Okay. It's interesting. So here we can calculate what would be the length for 3, for 9. So maybe what we can do, we can actually, for each node, we should get the deepest element. So let's call it DFS, and this DFS will return us the length, the height of our DFS. So we have a 3 node. If node equal to null, we return 0. Otherwise, we are going to DFS node left, and not right. And we return, I think here we should return depth, right? I think maybe you can have like a Boolean here, Boolean result. It would be true. And here what we will get, we check if mass if absolute value between L and R is greater than, so more than 1, greater than 1, then result would be equal to false. And here we have L and R, so we need to return the maximum depth plus 1, so it should be like mass maximum L and R plus 1. And here we will just call this DFS function for root and return results. Let's check. Okay, so here we have false, but we should return true. Let's take a look at this tree. So first we are node 3, so then we go to 9. So from 9 we get 0 and 0. And here should be less. Yeah. Yeah, and we are done. So let's check our previous implementations. Yeah, so here you see we got depths from left and from right. And then call it here. Yeah, I think this one is like much worse. And even we see from the implementation that it's 2 milliseconds. Here it's 15 milliseconds. Also like super bad. Then we have 0 milliseconds. And this one, yeah, it's fast but not fast too much. Here we have like this result that we actually currently implemented. I think here we even can't just return and break because we don't need other implementations. So for example, if it would be like this, then we just return all this stuff. I think it should be even faster. Okay. Yeah, it's still 0 milliseconds, so we cannot compare, but at least on memory it's less, because probably we didn't go too much depth with recursions. So I think that's it for today. Thank you. See you tomorrow.